throw a ball straight up, it leaves your hand fast, slows, and for one instant at the top, it has no kinetic energy at all. Yet on the way down, every bit of that motion returns and the ball arrives at your hand with the speed it left. The energy was never lost, it was banked. This video defines mechanical energy, the sum of kinetic and potential energy, and proves exactly when that sum stays perfectly constant. We already hold two pieces of bookkeeping. The work kinetic energy theorem tracks delta K, the change in kinetic energy of every body in the system, and for each conservative internal force, we define the potential energy whose change, delta U, is the negative of that force's work. Now combine them, define the change in the mechanical energy of a system as the sum of the two. Delta E sub m equals delta K of the system plus delta U of the system. Nothing is conserved yet. This is only a definition, a name for one combined quantity we agree to track. Now impose two conditions. First, the system is closed, no energy enters or leaves across its boundary. Second, the only internal forces doing work are conservative ones. Under those conditions, every joule a conservative force removes from kinetic energy reappears by definition as potential energy, and the total change in mechanical energy is zero. Delta E sub m equals delta K of the system plus delta U of the system equals zero. That equation is the conservation of mechanical energy. Rearrange it and the trait becomes explicit. Delta K equals minus delta U. Kinetic energy loss is potential energy gained, joule for joule. Neither condition is optional. Friction inside the system or energy flowing in from outside breaks the equality. Here is what those conditions buy you. We proved earlier that a conservative force does zero net work around any closed path, so run the system through any journey that returns it to its initial state. Same position, same configuration. The potential energy change is minus that conservative work, so around the closed path it is zero. The mechanical energy change is zero because the system is closed and conservative. Therefore, the kinetic energy change is zero too. Every joule that was parked as potential energy along the way has been paid back in full. Along the journey, kinetic energy may convert into internal potential energy and back, but nothing leaks. We call such a system one undergoing completely reversible processes. Run the film backward and it is equally valid physics. Now make this concrete with the most familiar case. An object of mass m sub o falling near the surface of the Earth, which has mass m sub e. Choose the system carefully, not the object alone, but the Earth and the object together. Inside that system, gravity is an internal conservative force, and the potential energy belongs to the pair, not to the object by itself. We specify a state by the separation between the object and the Earth's center of mass, together with both velocities. Both because by Newton's third law, the object pulls the Earth upward exactly as hard as the Earth pulls the object down. The Earth accelerates too. So the system's kinetic energy change is the sum of the changes for each body. For the Earth and for the object, each one half its mass times final speed squared, minus one half its mass times initial speed squared. Here the Earth's enormous mass rescues us. The gravitational forces on the two bodies are equal and opposite, so during the fall the Earth gains the same magnitude of momentum as the object. But kinetic energy is momentum squared over twice the mass, so at equal momentum, the heavier body carries far less kinetic energy, less by the ratio of the object's mass to the Earth's mass, more than 20 orders of magnitude for anything you can drop. The change in the Earth's kinetic energy is utterly negligible, so the system's kinetic energy change is, to superb approximation, just the objects, 1/2 m sub o times final speed squared minus 1/2 m sub o times initial speed squared. Now build the function we will use for the rest of the chapter. Measure height y upward from the surface and take the near Earth's gravitational potential energy we derived earlier m sub o gy with the 0 chosen at the surface, so u of 0 equals 0. Define the mechanical energy of the system as kinetic plus potential. E sub m equals k plus u, which is 1/2 m sub ov squared plus m sub o gy, one function of the object's speed and height. The change in mechanical energy between any two states is final minus initial, the quantity k sub f plus u sub f minus the quantity k sub I plus u sub I. When no external force does work on the system and no internal force is non-conservative, that change is 0, so the mechanical energy is constant. E sub m final equals E sub m initial. Equivalently, k sub f plus u sub f equals k sub I plus u sub I. Evaluate kinetic plus potential once at the start, once at the end, and set them equal. That is the working equation the coming examples build on. Watch the working equation in action as the ball falls, writing m for the object's mass. Height shrinks, so potential energy mgy drains, speed grows, so kinetic energy 1/2 mv squared fills. At every instant, the two bars sum to the same total. That is the whole content of conservation of mechanical energy for a closed system with only conservative internal forces. Kinetic and the potential energy trade places and the sum never moves. Keep the checklist in mind. A closed boundary, conservative forces only. The next videos put this to work on energy diagrams and then confront the case the checklist excludes. Friction, where mechanical energy is no longer conserved and the accounting must widen. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.